Hello! We're back with random math, and this one is actually part 1. There is going to be a part 2, and we're focusing on non-elementary integrals. You might recognize this integral, the integral of e to the negative x squared dx. If you do recognize it, you'll know it from the Gaussian integral, which if you integrate this function from negative infinity to positive infinity, you get the square root of pi. But what if you just integrate it? See, the reason why you have to square the integral, you have to convert it into polar coordinates and then do that whole thing. We have to do these complicated steps instead of, regular integral solving because the function actually has a non-elementary integral. And that means it cannot be expressed in finite algebraic terms. And so what we're going to be doing in this video is solving for the integral, but in its infinite form. Like not just putting non-elementary, we can't freaking do it. We're going to actually solve for the integral of e to the negative x squared dx using summation notation. First thing I notice, this is e to the power of a function. Recall e to the power of x just equals the sum from n equals 0 to infinity of x to the n over n factorial. So we're just going to plug that right in. Integral of the sum from n equals 0 to infinity of, in this case, x is negative x squared, so we'll just put that in there. Negative x squared to the n over n factorial. Don't forget your dx. Now, there's something I would really love to do that would make my life so much easier, and it would be to swap the sum in the integral signs. But we cannot do that until we prove that the sum is uniformly convergent. What is uniform convergence? It just means that if you take the partial sum of, this summation and you keep adding enough terms, then the error between the series and the actual function can be made small everywhere on an interval. Let's prove it's uniform convergence. Yes, we're doing this. Usually you'll see math YouTubers, for example, Dr. Payam doing integral from 0 to 1 of x to the x, and Dr. Trevor Bassett doing this exact same thing with the exact same integral. And it ends up being proven that the sum is uniformly convergent because at the end you find out that it's absolutely convergent. Anyways, we're going to not just assume that it can work. We're actually going to prove it right now. Let me just do a little bit of simplification. This right here is negative 1 times x squared. So I'll kind of like distribute that this power. All right, so we just have the function inside the sum. We're going to do what's known as the Weierstrass M-test. I'm pretty sure I butchered that freaking pronunciation, but I tried my best. We're going to let this entire thing equal f sub n of x. And we're going to take the absolute value of each side. So the absolute value of f sub n of x equals, if you take the absolute value of a fraction, you can kind of just like push it on the numerator because n factorial on the denominator is positive, blah, 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 equals the absolute value of negative 1 to the n x to the 2n over n factorial. And because this negative 1 to the n is kind of, how like the terms like switch from plus to minus, plus to minus, plus to minus, because there's an absolute value, it's just going to stay positive all the time. So this is just equal to the absolute value of x to the 2n over n factorial. Now, to continue, we're just not going to care about anything. We're not going to care about any discouragement. We're not going to listen to the outside world. And we're going to say that x is inclusively bound between negative a and a. Therefore, the absolute value of x is less than or equal to a. Less than or equal to because it is inclusively bound. Here's what we're going to do next. We're going to replace the absolute value of x with a. This is possible because, again, less than or equal to. But if we do so, then we're basically going to express like the maximum value of the function on the right. And because this is equal to this, then this will be less than or equal to this when you replace the absolute value of x with a. I tried my best to explain it. So the absolute value of f sub n of x is less than or equal to a to the 2n over n factorial. And then what we're going to do is we're going to take this what we're going to do is we're going to take this, and we're going to take the infinite series of that and see if it converges. The sum from n equals 0 to infinity of a to the 2n over n factorial. Let's separate these powers. The sum from n equals 0 to infinity of a squared to the n over n factorial. And would you look at that? That looks exactly like the expansion for e to the x. This is just e to the a squared. Therefore, this sum converges. Therefore, the sum we had in the beginning uniformly converges. There we go. We finally proved it. Gosh darn it. We can finally flip these two signs. So you have the sum from n equals 0 to infinity of the integral of -1 to the n x to the 2n over n factorial dx. Next, what we're going to do is we're going to bring everything that is only in terms of n outside of the integral, because we're integrating with respect to x. And anything in the n world is how Black Pen Red Pen would say it. It doesn't matter in the integration x world. So this is equal to the sum from n equals 0 to infinity of -1 to the n over n factorial times the integral of x to the 2n dx. Then we just integrate that using the inverse power rule. So you have the sum from n equals 0 to infinity -1 to the n over n factorial times x to the 2n plus 1 over 2n plus 1. And we're not going to put plus c yet. We're not going to put it in here, because then it'll be, changed by this product. So we have to add c after the fact. So we're just going to multiply everything together to get the sum from n equals 0 to infinity of -1 to the n x to the 2n plus 1 over n factorial times the quantity of 2n plus 1. And for the sake of being clear, we don't want to add plus c right in front, because you don't know if that's part of the summation or not. So we're going to add c plus. And that is actually our final answer. This is the integral of e to the -x squared dx. And actually, there's a better way to define the indefinite integral of e to the -x squared. For that, we're going to talk about the error function, erf of x equals 2 over the square root of pi times the integral from 0 to x of e to the -t squared dt. Because e to the -t squared, if you think about it as a function of t, is a positive function, this whole thing is just the integral of e to the -x squared dx. 2 over root pi times the integral e to the -x squared dx equals error of x. I'll just call it error of x. And then we simply solve for the integral part. So we'll multiply each side by the reciprocal of 2 over root pi, or root pi over 2. And therefore, the integral of e to the -x squared dx equals root pi error of x over 2. And then, for the sake of the indefinite integral, we're going to add plus c. That is also the answer. Well, guys, that is it. Thank you so much for watching, and I'll see you guys in part 2 of non-elementary integrals. Goodbye.